Adam from the University of Massachusetts, Boston. I'm a physics major finishing up my degree, and I've been inspired to get into machine learning engineering for bioinformatics. And what inspired me was my statistical mechanics class. I wrote a bunch of models for it in lieu of a PowerPoint presentation that I really didn't want to do. And a procrastination became a project, became a passion, and it's now become a career. I'm fascinated by these agent-based models, whether they're stochastic or purely deterministic. It's amazing to me to watch these things play out. And one of the things that I noticed when I was writing the models was, gosh darn it, wouldn't it be great if the computer could respond to the output and fiddle with the input and get you where you wanted to be. And so this is the culmination of all of my research into it so far, and it's something that I call APE, or automatic parallel exploration. So I'm sure you've all heard of the idea that if you got a million monkeys on a million typewriters, they could eventually bang out the works of Shakespeare. But that's random, and you really need a lot of monkeys. What if you could replace them with apes? They're smarter after all, more dexterous, and can use tools. Specifically tools like machine learning. So imagine that a group of apes got together and distributed among themselves a bunch of initial conditions for the runs of the same simulation. And the apes went and they ran the simulation, and they looked and they used their machine learning tools to analyze the outputs of the simulation and compared them to the target that was shared among all of them. And the one that got the closest, once they got back together again to discuss, would seed the distribution of the next batch of runs. And this process would continue, very much like evolution. Only the apes get to live. Very much like evolution, until the model got to the final state that was desired, the target. And once that were done, its seed, the set of initial conditions that led to that run reaching the target, could be established in a laboratory setting, allowing you to have a verification of it. And you're going to find out one of two things. Either one, that your model is right and you can achieve what you want, or two, your model is wrong and you can't. So this is a really, really useful thing in bioinformatics, specifically in tissue engineering, where we find a lot of.
There's something interesting in fire service. The United States spends
where we find a lot of models. Could you mute Antonio, please? Thanks.
Yeah, go ahead. Sorry about that. Yep.
So where we have cells that are playing with each other on a scaffold in a broth, but they're not playing nicely with each other, and we can't really figure out why. Well, one of the approaches in machine learning that we can use is something called reinforcement learning, which is what I've described with those apes. And if we could apply it to those simulations of the cells, then we could run a whole bunch of experiments virtually, and then put them to the test. So this is our problem, right? Because doing that manually is really expensive, right? We have to have a lot of researchers sit around and say, well, maybe we could fiddle with this, maybe we could fiddle with that. Let's try this, throw it on the supercomputer. Okay, that didn't work. Here we go again, 2 weeks later, and everybody's, getting their salary, getting their health insurance, all those costs of employment, turnover, all of that. It's a lot of money. If you could parallelize it, you could save a lot of cash, but also you could work a lot faster because the machine can work around the clock, whereas a team has to sleep, right? And you can also get, with the cloud, a heck of a lot more computation, right? So I think I should have been moving through slides a little more quickly. Here's the average bioinformatician salary range. Okay, $76,000 to $98,000, and the health insurance. So it's 30 to 60, 38 to $60 reasonable total hourly cost of employment before overhead. Right? Computers are cheaper. A pricey cloud computing cluster costs about 24 bucks an hour. And I literally went just to the Oracle website and just scrolled and scrolled and scrolled and scrolled and scrolled until I could find the priciest one I could find. And literally nothing on that entire website could cost more than hiring a person, right? And you have to not only hire them, but you've got to train them, manage them, retain them with bonuses and stock options. It's really expensive and it's slow, right? If you have a problem, you can apply compute immediately rather than having to scale up a staff because progress just isn't where you want it to be. And you also reduce the exposure of intellectual property. You're not going to have someone going, ooh, you know what? I think I know. I think I have the right guess, and then run off to another company and make some guesses and get a bunch of money there, and you miss out, right? So here's another annual cost example. Really, I'm trying to hammer this point home. If you had one senior and four juniors, right, and another team, that's $852,000. If you compare that to an automatic model exploration team of one senior and four juniors, but just one team, and 2,000 hours on four pricey clusters, you're going to get a, oh boy, I cannot minimize this Zoom thing. Oh, that's annoying. I can't read the right side of my screen. But anyway, it's about $250,000 cost savings. But moreover, you could take those two teams that were doing manual work and give them each a cluster, which is much cheaper than a team, and get twice as much work done or more. Now, this is not some sort of pie in the sky dream of the bleeding edge. There are mature, scalable libraries to make this happen. There's Dask, which automatically and massively parallelizes data access and computation, and Teapot, which automates machine learning model selection where expertise is limited. Now, the important thing is that both of these are industry standards in cluster scale computation. You use them in data centers, you use them on the cloud. And I'm going to now show you some pictures of how these libraries work, because a picture is worth 1,000 words. Okay, so you can see that Dask starts at this input. This is a picture of Dask, and it bootstraps and it goes to a certain depth of calculations. And here it's just estimating, and it all comes down to the output. And the beautiful thing about it is that it's completely automatic, right? Even something this complicated, you can construct with very simple idiomatic Python code. You do not need a master's degree in data science to figure out how to use Dask. I myself wrote the toy model of what I'm describing in pure Python, and it took me much longer to do that than it did to learn Dask, which I was able to do in just a few hours. Okay, now this is Teapot. And Teapot starts with raw data, and you're going to have to do the data cleaning yourself, but it will do the feature selection, the feature pre-processing, the feature construction, right? Where you're figuring out what's important, cleaning up that bit of the data, building it into something that you can do machine learning on, and then run a whole bunch of models in parallel and pick one. But the great thing is that with domain knowledge, right, where you know something about the data, it's not blind, because Teapot flies blind. You can start to pick these models from the beginning with someone. This is why, while I am talking about replacing some human labor, I'm not talking about replacing humans. This is about technology making people better, stronger, able to do more than they were in the past. Now, this only is getting better. Not only is the machine learning science, which I'm just not going to get into because it's too complicated, advancing and becoming more efficient, but the underlying hardware is improving too. You see, the more complicated that a model is, the more expensive it is to run, but not linearly. It's more like quadratically. So if it's 10 times more complicated, it's 100 times more compute that you would need to do. So we already have things called quantum computers, which basically flatten that back out to a linear progression because they get work done at about the square root of the complexity. But we're actually expanding them now. They're available on all major clouds. There are businesses working with them all over the world, and there is a Python library that lets you do not just like assembler level where you're fiddling with the individual pieces of the program, but you can start to do higher level programming like if, then, else, for loops, while loops, you name it. You can really start to program and really start to write simulations. So over the coming years, we're going to see more and more complicated simulations become computationally feasible. And it's going to not just be in the ivory tower, not just for the privileged few who can get time on a supercomputer. It's going to be on the cloud. Every major cloud provider is chasing, every major cloud provider is chasing this as fast as it can. And if it isn't already there, it's getting there. Google's chasing it. Amazon and Microsoft are already there, right? And they are mature, robust, and scalable, and they're only getting better. You've got quantum annealing hardware, ion trap devices, superconducting, you name it, they got it. They've got easily a dozen manufacturers each supplying hardware. So this brings us to a solution that is going to become apparent over the coming years, which I, again, want to really reiterate. It's to define the goal as the state of a bioinformatic model or any model that has a lot of inputs and a lot of outputs and is a long, complicated black box, or it can be clear, but the point is that it's not something that you can do by hand. And you define it as the state of that system, like the cells playing nicely with each other, forming quora, growing, multiplying, they're going to the right places, they're emitting the right secretions, and then to explore the model automatically by letting generations of initial states, and I guess there's a little typo, develop. And then you use machine learning to identify successful steps toward the goal from batch to batch, unsuccessful steps away or dead ends. And you can see that it's very much like you're guiding someone through a maze, right? And you adjust the initial state of the model based on weights, biases, and chosen algorithm to move toward the goal. So we're going to go from this hideous abomination of cells toward something like heart tissue, so that if your heart is failing, it could be replaced, if not in whole, at least in part, and you could go on living, right? So let's talk about this idea of a goal as a state. Manual exploration defines the goal in qualitative, abstract terms, right? We want what we want without anything that we don't want. But automatic exploration defines the goal in quantitative, concrete ones. The model is doing this and not that. We've explicitly spelled it out. And yes, we can have abstractions that make it easier for humans to work with it, but the machine will have those hard constraints, right? And we need a different set of initial conditions. Running the same model over and over again just lets us explore what random chance does. We want to see what our own little changes in behavior can do, right? And we'll do that by having distributions for each of these variables, and we'll sample from them to create each generation based on the seed, which would be chosen manually for the very first step, and then based on the most successful simulations, the ones that got closest to the goal. The ones that got closest to the goal in each subsequent step, right? Then we have machine learning selection. We've evolved the generation for a little while. We check elimination conditions. So to save computing power, one of the things we can do is identify when a model is going completely off the rails and just kill it. We don't need to keep simulating something that's never going to get to where we need it to go. And then we would have selection conditions, right? let's say that it's really simple. We want them to secrete as much, I don't know, as many red blood cells. We want the liver to crank out as many red blood cells as possible, right? The ones that make more red blood cells, those runs of the simulation will be deemed more successful than the ones that didn't, and their initial conditions will be used to seed the next generation, the next batch of simulation runs, right? And once we have that seed, we seed the new generation, and we repeat this again and again and again. And that's why you need the cloud, because this needs to be parallel, not sequential, because we'd never get through it. And we need a lot of hardware. And it's finally cheap enough for us to do this stuff, not just the simulations, but also the machine learning and the deep learning that you can also do, which costs even more computing time, even more hardware, right? And what we're bringing is the power of simulating evolution by natural selection. So here's a simple demonstration for you. I wrote this in Julia because Julia is really the future of deep learning and of simulations. It writes like Python, but runs like C++. And I wrote a simulation where particles randomly walk through a bounded three-dimensional volume. And if they bang into each other, then they're going to form a product particle, right? There were two particles before, but now where they collided, there's just going to be one. And I extended the MLJ library in Julia to do polynomial regression over the number of both species over time. And so you can see how, for some reason, linear just won't show up. I tried to fix it, but you can see how you have the quadratic approximation and the cubic approximation. And then on the bottom one, you do see the linear one. And you can then, the next step is to time, you can see that this cubic equation, right, it's going to cross the x-axis. And if you wanted to do something really simple, a toy model, you could say, well, all right, I'll run the simulation until then because I'm not predicted to end yet, right? So here's an example of the guts of that simulation. You have a 3D environment where all the coordinates are integers, so you don't have complicated stuff like particle momentum and what angle they're colliding at. It's very, very simple, just to illustrate it. And I have a location dictionary to update everything. And throughout, the state is logged so that you have access to the inner state of the simulation. Because if you want to do time-wise analysis, then you're going to need all of those states, right? And here's the code that I use to do the n-term polynomial regression. And ultimately, you predict reagent exhaustion. And importantly, this is getting a little bit more into the machine learning science. Even polynomials may not ever cross the x-axis. You need to pick an odd one to guarantee it has at least a chance of doing it. And that means that you just have an odd power in the polynomial. So x cubed, x to the fifth, x to the seventh, x to the ninth, not x squared, x to the fourth, x to the sixth, x to the eighth, right? And then you run the simulation again to see if the reagents have been exhausted, right? Now, here we get to the architecture, right? You start with that seed, same idea for this, which is how long is it going to take to exhaust the reagents? You come up with a distribution, you analyze in parallel, you choose which one was the closest guess, and you repeat until you're within the tolerance that the user has set. So this right here, this architecture is the key to making this work. Dask is the library that could make it work. And cloud computing and ultimately cloud quantum computing would be the hardware that it would run on. So all of this stuff is either here or going to be here very soon. And it's a huge opportunity for the entire bioinformatic and especially tissue engineering industry. But this can be applied, like I said, to any kind of model that has these same constraints. A lot of inputs, a lot of outputs, complicated process in the middle, takes a long time to run. If you can do that in parallel batches and learn from each one and seed the new generation, applying reinforcement learning to go from batch to batch to batch, you can evolve toward the state that you want to figure out the inputs that you need to get that output in real life. Then if you're right, great. If you're wrong, well, then the model must have been wrong. And that is a discovery in and of itself. And then you can go back and start from square one and see if you get it right again. So from here on out, I hope that you would be comfortable going into some breakout rooms to discuss the demonstration and possible applications of the automatic exploration of bioinformatic models, considering pitfalls, obstacles, dangers, and brainstorm possible workarounds and adaptations. And I'm certainly going to be applying Dask to my toy model that I wrote in pure Python. I'm thinking of posting the source code at some point. I'm not sure if I want to yet because it's not documented well. But I would love to know from you after you're done what you thought, and propose a topic within this subject that you would like me to talk about next. So thank you very much.
Well, thanks a lot, Adam. So we could try breakouts, or we could possibly just stay in the room and if people have questions, ask those. Or unless Adam, you want to provide any more direction, we could try just doing it in the main room. What are your thoughts on that?
I think it would be pretty tough, just considering how many people are here, for everyone to have like a fair chance at a discussion. But it's your meetup.
Why don't we? Well, because I don't know how many people are going to be participating offhand. So that's
that's a good point.
Keeping it. Why don't we start with the main room, and then if it gets chaotic, we could potentially break things into the. We can go do breakout rooms. So I have a question though for you. What you're describing here sounds a lot like hyperparameter optimization as a general problem. Have you looked at some of the libraries like scikit optimize or hyperopt or any of these things to when you say the inputs to the model, are you envisioning those as being the sort of hyperparameters, or are there other inputs that you're talking about there?
I'm talking about the oh, by the way, we're still recording.
Yeah, that's okay.
Okay. I didn't know if you just wanted the simulation. So I'm not talking about the inputs to the machine learning model, because we often throw around model. I'm talking about the simulation itself. So, where am I putting the cells? How many am I starting out with? What's in my broth? What chemicals am I putting in? Those are the questions.
Those sound like hyperparameters to me. Are you, so in the reinforcement model, so you're using a reinforcement learning pattern here. Do you, what's your approach to selecting the model for learning those inputs?
So there's two ways to do it. For toy models, it's pretty obvious. So I did this for X cubed. I did it for like a toy protein folding model. And I just said, okay, I want the protein to loop back on itself. But if it's an open question and no one really knows, Teapot at least gives you a fighting chance at having a model. But it's also true that there's a fair bit of domain expertise in bioinformatics or whatever field you want to apply it to. And you can get some guidance from domain experts. And that usually is better than just hoping that Teapot will pick the right thing. But you're not completely out to lunch if the experts can't help you.
Hey, Adam, I had a question for you. So what I understand is that the underlying architecture is a reinforcement learning to reach to a goal which you have set forth with the model, right? But
Correct.
Teapot will only going to actually expect you to try different hyperparameter states to reach that model. But if there are different states, I know reinforcement learning is pretty much like a little bit like dynamic programming, I guess, like something similar. But if those states in between, are they going to be defined by Teapot, or it's more like you need a structural knowledge of the things, like, you should be an expert in bioinformatics or something similar to get to the states in between?
Right, and that is the long run goal of this, if you're going to be starting a new division within a company or starting a new company altogether, you're going to need to, just like we will in the future of any kind of machine learning, that it's not just going to be in the laboratory, but it's going to be applied to a real world problem. You're going to need to bring together people with the expertise in not just the software, but also the domain itself. So that is where you would need the experts. And I don't think that this can replace expertise. I think it can augment it and accelerate the progress that it delivers, much in the same way that we still have farmers. They just use combine harvesters rather than sickles.
And in this whole thing, quantum computing is more the tool, right?
Correct. It's the platform, and it enables having much more complex models populated with many more particles and cells. So you can get a lot higher fidelity simulation if that ends up being the sticking point for you. And you can also do deep learning. And you can do things that just aren't possible otherwise. For example, the classic case is cracking RSA, which you can do with a quantum computer, but you can't do with a deterministic Turing machine.
Okay, got it. I have two other questions. One is a little bit more, general question. How do GANs play in this scenario? Like, let's say if you want to simulate stuff, you can probably do that using GAN by creating some artificial data. So does artificial data play a part in this area? That is the first question.
So are you saying to uh, rather than run the simulation, have a GAN that tries to guess what the simulation will spit out?
No, the GAN would be providing, let's say, a starting artificial, instead of having one set of inputs, you have a different set of inputs generated by GAN. So you don't probably even require humans to generate a set of inputs.
Well, correct. I mean, when this process isn't entirely parallel, it converges back once all the simulations are done, and then you choose the one that got the closest. So that
Okay.
would be more of a reinforcement learning Bayesian approach rather than a GAN.
Okay. And one simple question regarding the tools is there a Dask library in Julia? Because Dask, I've heard it's only in probably Python.
So Julia has a library that lets you call Python libraries. Obviously,
Okay.
it would be ideal to have a Dask implementation in Julia so that you wouldn't have to use that duct tape and chewing gum. But since we live in an imperfect world, where we have zero indexing and PHP still exists, we will have to have probably some duct tape and chewing gum for a while. But that would be obviously ideal if we could have Dask plus Julia. These simulations could be written in Julia, making them much faster to implement, but also much faster to modify and much easier, because doing things in C++ requires you basically to be a computational scientist if you're a domain expert. Looking at Julia code and editing it, I mean, you kind of need to know how to code, but not to the extent of working with something like that.
Got it. Okay, great. Thank you.
Hi, Adam. This is Tim.
Hey,
I had a
Tim.
I had a question. So when you say simulation, are you referring to kind of a physics-based models?
I mean, it really depends on what kind of simulation you're working on. You could have a simulation that's actually quite, computationally light, but you still have to do a lot of fiddling with it, right?
Gotcha.
You could
Are
have,
you
on the other hand,
use
something that goes.
Okay. Are you able to utilize kind of a multi-fidelity simulations in your approach?
I mean, of course, it doesn't. What you're running on isn't really what limits it. It's just a question of building and scaling up this parallelization of it and figuring out a way to apply machine learning to it.
Right. So yeah, one of the questions I'm wondering is that not all simulation computational cost scales, as you mentioned before. So having a multi-fidelity approach is can be computationally very efficient if it's possible in your current approach.
Oh, sure. I mean, the sticking point would be if you have for example, are you talking about multi-fidelity across the model, like you're just turning down the resolution
Yeah,
in a
so
video?
you can use more, higher fidelity models with, higher computational costs or lower fidelity models. I'm saying this just as an example. If your physics-based model, this is, outside of the machine learning part.
Yeah, I mean, you could absolutely have a low fidelity model run, and then once that's validated, you could try it on the high fidelity model. So you could save yourself some computational cost there. And if you found that it works on the low fidelity model, but not on the high fidelity model, then you could try a high fidelity model run and see what that spits out. Or you could see what, alternatively, you could choose to fiddle with the low fidelity model to see what the heck the problem is and to see if you
Yeah.
can make it produce the same result. But the reason I mentioned whether you're talking about across the model or sort of multiple fidelities living in one model is that in finite element analysis, for example, you can have a high resolution where it counts, right? Like, say, someone's face, and a low resolution where it doesn't, the car frame.
Right, right. Yeah, so one of the things that basically I'm getting at is, one challenge is with like these simulation-based approaches and combining that with machine learning is that, of course, you're relying on the accuracy of the numerical simulation. And so how do you account for the errors and uncertainties in the numerical simulation? And how does if you have, like I say, experimental data, how does that come into place, for example? So, whether you do kind of like selective sampling based on these large number of simulations that you're going to do, and then uh, things like that. So what is your kind of, how do you integrate the simulation uncertainty error, and where does the experimental data come into in your approach?
So obviously, like you said, this affects any simulation, whether you're trying to apply this approach to it or not. So if the sim ends up having, say, a lot of error accumulation, then it's probably just not a very good simulation to begin with. On the other hand, because you are killing the simulation at the end of each batch, each sim is going to start fresh. So it's not like you're taking the final state of the simulations of generation one and making them the seeds for the making them the seeds for the simulations of batch two. You're taking the initial conditions of batch one and using them to seed the distribution of initial conditions for batch two, and so on for batch three and four. And you're choosing the simulations that were the most successful to do that seeding with their initial conditions.
Okay,
I really feel like an illustration might make it a little bit more obvious what I'm talking about, and I regret not having made one.
That's okay. Thank you.
Yeah, it's an interesting general problem because I think there's a lot of cases, there's a lot of applications and domains where simulations would make sense, but they're not, because it necessarily involves a domain expert to reason through an underlying process. And it sounds like you can't really, Adam, you can't really do this work without a simulation. It's not like you're just going to go model a bunch of data and sort of optimize for for some predictive accuracy. You're really looking for to sort of validate a domain approach, a domain informed approach. Is that
Yeah,
fair?
absolutely.
This is sort of a general approach that I think is missing in a lot of classical machine and deep learning applications. Because my instinct here is to say that the deep learning lesson from vision has sort of skewed a lot of points of view here. It says we can just take a bunch of observations, crank them through a really deep model and get a great predictive model, get an accurate model, but you lose, well, you never ever get a handle on why. Well, in some cases you do, but the problem with the deep models is that it's a constant struggle to explain why they perform well or why they perform poorly. And it used to be that there were vision domain experts that would, sort of specialize in feature engineering, across all sorts of different tricks and applications. And then deep learning came by and just wiped everything off the map. And so it's tempting to think that's the pattern that we should throw use to solve every conceivable problem. And I just don't see the simulations, even to Ravi's point, when I hear simulation, I do have a Pavlovian response. Is there a GAN involved someplace? Is there an autoencoder involved in this case? In your work, could you describe a little bit more about the process of the domain expert and how that individual, maybe it's you or someone else, how they interact with the model and use the results of the experiments to feed back and not just adjust the hyperparameters or the inputs, but also the model itself? Maybe setting Teapot aside and some of the auto ML stuff aside, how have you seen the simulation model tweaked and evolved based on the machine learning methods?
Okay, just to get the vocab clear, when you say model, are you talking about the simulation or are you talking about the machine learning?
So I'm talking about the simulation.
Okay, so for example, let's say
so actually I'm talking about both. I'm talking about the model being
Yeah.
used to inform the decisions used to create and then adjust the simulation. The iterative process is what I'm talking about. So it's actually both.
Yeah. So let's say that, make a really simple toy example. You had a simulation of light that said that the intensity of light at a distance is equal to the inverse of the distance. That's obviously not true. It's the inverse square. And if you ran this through ape, then you would get a seed that would tell you, where you needed to be to get a certain intensity of light from a certain a light source with a certain luminance. And then you would try it in real life and you would find, oh my gosh, I'm basically in the dark. How can this be? Right? So it's not ape's fault. Ape did the best that it could. Ape is not very smart. It does not have a PhD in your field of, electric lighting. You are going to have to say, well, it seems to me like this just isn't so, right? I've got this seed, I've got this model, I've got the simulation. The simulation says this is going to happen, right? And that simulation is the same simulation that ran through every single batch. The simulation itself is unchanged from batch to batch, just the hyperparameters are getting tweaked. So that means that that simulation is wrong. You're going to have to change it. You're going to have to start from scratch, right? That is a discovery. You can publish that. It was worth the money that you put up. On the other hand, yeah.
No, go ahead.
On the other hand, if let's say that your simulation was right, you did use 1 over x squared, then you would stand right where you needed to be in the light, and you'd say, oh my gosh, ape accelerated my research so much, and then you could publish that. So you're going to learn something either way. You're either going to find out that your simulation isn't up to snuff, or you're going to find out that it is, and holy cow, we can now grow heart tissue, or holy cow, I know how to better refine silicon, or whatever it is that you're trying to apply this approach to.
Yeah, that's a great sort of short tight summary of this dynamic. In that particular case, when you do discover that your observations are not lining up with what you expect, what is the process of the domain expert? Is the domain expert intimately familiar with this entire pipeline, or does he or she? How do you involve? I guess this is more of a process and a human problem that I'm talking about. How do you get that domain expert to plug back into the simulation? Is it really just a matter of sort of understanding the algorithms and the assumptions and the encode, the functions that are being applied and reasoning through them, kind of old-fashioned debugging, the application of math and science. Is it just that, or are there other methods of teasing out correct behavior in the simulation?
I mean, again, answering that question would, in some sense, require having knowledge of how, various simulations work. Some of them are really simple. Others are immensely complicated to the point that you have supercomputers running 60-year-old Fortran still going strong in the Department of Energy today.
So they have to be pretty
right?
plugged into this. This is something you want to collaborate with domain experts in from the beginning, so that you're not, I can imagine a situation here where you're running this and they have to be the authors of the simulator, in other words.
Yeah, absolutely. That's exactly the idea.
Yeah.
You collaborate with the simulation expert. You say, okay, you've got your simulation. You think it's good enough. Let's put it up against the ape. Let's see how long it lasts in the ring boxing the gorilla.
Yeah.
And if it comes out a bloody pulp, well, you aren't such an expert after all. If it comes out on top, holy cow, you beat the ape. You made a discovery. I mean, also, you could have made a discovery either way. If this is a very well accepted simulation, well, you found that it's got a bug.
It's funny that you mentioned Fortran and high performance computing. I did some of my thesis work on Fortran codes using high performance computing, and for those really large scale simulations with really nonlinear dynamics, there are many reasons why they fail. It's not always it's generally speaking, for those kinds of applications, it's really hard to determine why they fail. And your approach, may be challenging in those instances. But if the models are, if the numerical simulation models are very mature, then yeah, I think, it would be very useful for sure.
Yeah, I mean, once you start talking about the total insanity of like, oh yeah, I'm doing multiple petaflops of compute on multiple decades of Fortran because I'm Uncle Sam and I just have the money and the time. There's probably no cloud big enough to eat that. You're talking about putting up the ape against Godzilla.
Are there any other questions for Adam? Does anyone else work with simulations to generate predictions and input into models? I know of people who do this. I've actually never done it myself. This is not I actually build tools, so I don't do any of it myself. I have to imagine, for example, the cases that I'm familiar with are in the DOE, and they model nuclear. As an example, the state of warheads or nuclear matter that they can't otherwise test, so they have no option but to model and generate simulations and then to test those. So it's endemic to certain industries, and that's why you see these supercomputing installations in DOE. But other than that, I haven't seen a lot of this. I imagine it's quite common in biology and physics, and not your traditional computer vision problem, certainly.
I joined it late, so I just have a maybe dummy question. So it's the simulation and the machine learning. Are they trying to verify each other, or it's one piece of work but different? I mean, it's different pieces of one puzzle. You have to finish the machine learning and then do the simulation, in sequence or what?
So the machine learning is fiddling with the hyperparameters of the simulation.
Machine learning is fiddling hyperparameter.
I would describe that as a hyperparameter optimization problem, which can use all sorts of models under the cover to learn optimal inputs. It sounds like Adam, you're using an RL style model for that. The ones you generally see in the sort of really lightweight models tend to be Bayesian. Those are the ones I've worked with. I've never used RL. I guess that it would be RL in a way. I've just used very simple, the standard out of the box Bayesian optimization methods from like Optuna, HyperOpt, Scikit-optimize, those libraries.
Yeah, the reason that I think of RL is that it allows you to save programmer time, and it allows you to handle things that start getting really complicated quickly rather than having to, DIY. Because the goal is that you could ultimately, like I said, start a firm or a department within a firm that does this for bioinformatic companies, especially ones that don't have their own in-house staff to write these models. Because if startups and small bioinformatics companies that are doing development could get access to this, then they could greatly accelerate the pace of their research. And this is what fundamentally motivated me to, walk this long path toward developing this, is that there's a real human benefit to it. Because at some point, we're going to crack the genome and we'll beat aging, we'll beat cancer. In the meantime, we'll have thrashed all the various other things like Alzheimer's and Parkinson's, ALS. Those are finite problems. Eventually, if you just throw enough warm bodies and silver at them over enough time, you're going to beat them. And the one thing that can get you in the meantime is all the various menageries of diseases that are just too many to cure efficiently. And if your organ starts to fail and there's no transplant available, even if you would have lived to see the day that we could achieve biological immortality, you'll still die and you'll be dead forever, right? But the sooner we can move that date forward, which is the work of people much smarter than me, and the sooner we can move the date forward that we can repair and replace organs, because tissue engineering eventually becomes organ synthesis, the more of those people that we can save. And those aren't just vague people, those are people that we know in our lives, our parents, our grandparents, right? Maybe even ourselves, depending on how old we are. And it's absolutely necessary that this kind of work, this kind of research gets all the support it can get. And that's why ultimately I do want to do an ape startup and see how many companies I can help. And I'm doing as much market research and tech research as I can, looking at tech, deep tech startup accelerators, you name it. Because, my motto has basically become get busy coding or get busy dying.
It's a huge lever for sure. Any other questions for Adam? All right, with that, I'm going to stop the recording here.